To get a better feel for the null space of A, it's best to jump right in with an example. So we have a matrix A. We want to find a basis for the null space of A. So the null space of A, remember, is going to be all vectors x. Let me write it this way. The null space of A is equal to all vectors x such that A times vector x is equal to the 0 vector. Okay? So that means we just want to solve the homogeneous equation. The general solution of the homogeneous equation, where A is the coefficient matrix of that homogeneous system, that general solution will give me the format or formula for all x in the null space. Okay, so that's what I want to do first. I want to solve the homogeneous system. Well, to solve the homogeneous system, I just need to get matrix A in reduced row echelon form. Since the other side of the equation is a 0, I don't need to add an augmented part. We usually don't write the zeros. So I just want to use my calculator and get matrix A in reduced row echelon form. This seems to be a theme, doesn't it? Notice that for a lot of the information that we need here, if we could get the matrix in reduced row echelon form, it becomes easy to find. That's why we like reduced row echelon form so much. Okay, so let's get the reduced row echelon form of A. Our calculator's done the hard work for us. So the reduced row echelon form of A is equal to, first row is 1, 0, negative 26 over 31, negative 1, negative 7 over 31. Second row is 0, 1, negative 2 over 31, 0, negative 22 over 31. And last row is all zeros. Okay? So let's first characterize the general solution to the homogeneous system of equations. So again, imagine that augmented part is all zeros. Okay? We need to solve the system. And now that it's in reduced row echelon form, we can. Remember, each column corresponds to a variable. So let's solve the system. Note, by the way, how many free variables we have. Any column that doesn't have a leading entry in it corresponds to a free variable. And so in this case, my only 2 leading entries are these 2. So the last 3 columns will all be a free variable. So I have 3 free variables for this system. All right. So let's call x5, x4, x3 my free variables. So x5, let's call it t. x4, we're going to let be the free variable s. x3, maybe we'll let that one be the free variable r. Okay, and then I could describe my other remaining variables in terms of these free variables. If we look at row 2, we can use that to help us figure out what x2 is. So row 2, I have the equation 0x1 plus 1x2 minus 2 over 31x3, but x3 is r, so I'm going to plug in r, plus 0x4 minus 22 over 31x5, but x5 is t, so I'm going to plug in t in place of x5, equals 0. And so if I get x2 by itself, I get 2 over 31r plus 22 over 31t. I just added these 2 terms to the other side of the equation. And for row 1 will help me learn about x1. I can solve for x1. Okay, so I get 1x1 plus 0x2 minus 26 over 31x3, but x3 is r, my free variable r, minus 1x4, but x4 is equal to my free variable s, so minus 1s, minus 7 over 31 x5. But x5 is equal to my free variable t. So if I solve for x1 by moving these three terms to the other side, I get x1 is equal to 26 over 31r plus s plus 7 over 31t. Okay? So that characterizes the general solution. Let me write it in vector form because it's going to make things a little bit easier here. Okay, notice that in none of these do I have any terms without any variables. When solving a homogeneous system where there's all zeros on the other side, the entire solution, it'll either be all 0, 0, 0, 0, 0, 0, or every term will have a variable. Okay? So I have three variables. So R times a matrix, or times a vector, plus S times a vector, plus T times a vector. Okay? So for x1, I have 26 over 31R. So 26 over 31R plus 1S. So plus 1s plus 7 over 31t. So 7 over 31t. Okay. For x2, x2 is 2 over 31r. I don't have any s terms, so no s's. And then 22 over 31t. 22 over 31t. For x3, x3 is just equal to r. So I just get 1r, no s's, no t's. x4 is just equal to s, so no r's, 1s, no t's. And x5 is just equal to t, so no r's, no s's, but 1t. Okay? So this, any vector that I could express in this way is a solution to the null space. This is the general solution to this equation, and every solution of this equation is in the null space of A. Okay, so one way I could characterize the null space of A is equal to the set of every vector that can be described in this way (1, 0, 0, 1, 0). Two over 31, 0, 0, 1. Okay. So the null space of A could be characterized as the set of every vector that I could write this way, where R, S, and T are real numbers. Okay. Expand that a little bit so you can see all the way. Okay. But that wasn't the question, right? We didn't want to just characterize the null space of A. We wanted to find a basis for the null space of A. So that means a spanning set that is linearly independent. Well, guess what? We've already found it. Notice we've just said that every vector in the null space can be described as a linear combination of these three vectors. That's all this is, right? This is just a linear combination of these three vectors. And these three vectors are linearly independent. A dead giveaway is that they each have a value, a non-zero value, on a row that the other two vectors are 0 on that row. Okay, so there's no way I could get rid of something non-zero by multiplying a 0 and adding it. Okay, the only way I could get rid of this and this and this is and get the linear combination to equal 0 is if R and S and T are 0. That's the only way I could get a linear combination of those three vectors to equal 0. So the basis for the null space of A is just those three vectors. So by finding a solution to the homogeneous equation, we also end up finding a basis for the null space of A. Okay. By the way, how many vectors do we have here, and how do we get them? Well, we have one vector in the basis, one each for each of the each of the free variables, right? So I could look at this, and it might not be immediately clear what the basis for the null space is, but I know immediately I have three free variables, and therefore the dimension of the null space is equal to 3. Okay, we actually give this, the dimension of the null space, a special name. We call it the nullity of the matrix. The nullity is just the dimension of the null space, and generally it's going to be how many free variables the corresponding homogeneous system of equations has. In this case, that's 3.